Yeah, good morning. In this session, I would like to deal with doing some vapor liquid equilibrium calculations such as plotting Txy and Pxy diagrams. There are only two possibilities to determine this information, either by experimentation or by using thermodynamics. So I have taken 4 different systems to do these analyses. In fact, these 4 systems are taken from your thermodynamics. So let us see how to plot these diagrams using Aspen. So let me define all the components that I have in this: methyl ketone, toluene, chloroform, so on. MDK, toluene, then chloroform, then write this as chloro, then tetrahydrofuran, then 1,4-dioxane, what is that? Then ethanol. These are all the components we have. Adenosine, methyl ketone, toluene, chloroform, tetrahydrofuran, ethanol, and toluene. Okay. So having defined all the components that we are going to that we are plotting Txy and Pxy diagrams, what we need to do, you can see when you open Aspen, by default you will be performing property analysis, which includes pure property and pure component property analysis, binary property analysis, and so on. This is where you have Txy and Pxy diagrams, but unfortunately right now they are not highlighted. You will not be in a position to use them. So what is the minimum information that we require in order to do these calculations? You can see here, after defining the components, we need to select the property model. So you need to take a decision regarding the property method that is going to represent the vapor liquid equilibrium. So let me go to that step. For the time being, let me take one method, Chavo-Cedar. Now you can see highlighted. So you should be in a position to run this property model calculations. Click on this binary. Now you can see, first of all, let me plot the Pxy diagram. So by default, we are supposed to take the more volatile component as the basis for plotting Pxy diagram or Txy diagram. Now you can choose at whatever temperature you want to plot. By default, it is using 25, but whatever is the temperature, you can specify. Let me run. Now you can see the Pxy diagram is obtained. Remember, this Pxy diagram, you need to choose an appropriate property package in order to get an accurate result. What are you going to get from this Pxy diagram? Do you think MEK is more volatile? This is because x1 is equal to 1. Mole fraction of MEK is 1. So this is going to indicate the MEK vapor pressure at 25 degrees centigrade, whereas this is going to indicate the vapor pressure of toluene at 25 degrees centigrade. So the vapor pressure of MEK being higher than the vapor pressure of toluene, so this is considered to be more volatile. Now you can see the blue one is going to indicate P versus X. The green one is going to indicate P versus Y. For example, any point on the blue line, the system is exhibiting as a saturated liquid. Any point on the green line, the system would be a saturated vapor. Any point in between these two will be a mixture of liquid and vapor. And any point above this will be indicating a subcooled liquid. Any point below this is going to indicate superheated vapor. That's how the simulator will be calculating the phase condition of the system. For example, the given system for this composition, let us say, is available at particular pressure and temperature of 25. Take this kind of a point, now it is going to indicate a mixture of liquid and vapor. So how are you going to decide how much part of this is going to be liquid, how much part of this is going to be vapor? So out of these 3 points, saturated liquid, saturated vapor, and the present condition of the system, you can use a lever arm rule to calculate the percentage of vapor and percentage of liquid, right? So this is one. Uh, in addition to this, what you can do is, now can you show me from this whether the system is going to exhibit positive deviation or negative deviation from Raoult's law? In case of Raoult's law, if you join P1 sat with P2 sat, it should form a straight line. So in case if you draw the line, if this particular P versus X is going to lie above, we call it as positive deviation. Below, we call it as negative deviation. But it may be difficult to infer that information graphically. But we can always find out this from looking at the results. Now you can see these are indicating gamma 1 and gamma 2. MEK is component 1, toluene is component 2. As you can observe, gamma I with respect to both MEK and toluene are greater than or equal to 1. So this is a characteristic for systems exhibiting positive deviation from Raoult's law. In fact, you will also be able to plot other plots from this. Let me plot this Y versus X. Now, this is going to represent the mole fraction of MEK in the vapor phase, mole fraction of MEK in the liquid phase at a temperature of 25 degrees. Do you think you will be using this Y versus X to determine the number of stages in a distillation column by Pxy method? This is not useful because column there will be a variation in temperature from top to bottom. So this is not the one you will be using. In fact, you will be using Y versus X at a constant pressure. Okay. That you can probably verify. Then I will go back to the input analysis. Now probably you can also do this. What will happen if I increase the temperature? You can compare how is it going to behave at different temperatures. Now you can see this is at blue is at 25 degrees centigrade. This is at 50 degrees centigrade. I think you might have done these calculations even in your thermodynamics. You will be in a position to evaluate the P versus X, P versus Y, and so on. Apart from this, probably let me also show you at one temperature. For example, I take a system with 50% mole fraction of MEK and 50% mole fraction of toluene. So what is this pressure indicated by the point on the green line? So in other words, what do you call this pressure as? So this is going to indicate the dew point pressure, because any small reduction in pressure from this point will result in the formation of first drop of condensate. Similarly, you can see this is going to indicate the bubble pressure, right? Any small decrease in pressure from this level will start forming the first bubble of vapor. As you can see from this diagram, bubble P is always greater than dew P for a given composition at a particular temperature. Now, in the same way, we should be in a position to plot Txy diagram. You can change the pressure if you want, or plot this at whatever pressure you would like to use. Now, one simple observation that you can make in the case of P versus X is above P versus Y, whereas in the case of Txy diagram, T versus Y will be above that of T versus X. In the same way, the same information can be obtained from this plot as well. For example, if I take once again 50% liquid, 50% MEK and 50% vapor, now what is this temperature going to indicate? This is the bubble T, and this will be your dew T, right? You can see dew T is always higher than bubble T for a given composition. Now once again, you can go into the results and observe what are the values of gamma. Once again, you can confirm that it is a system exhibiting positive deviation from Raoult's law. In the same way, you can also plot Y versus X. Remember, this Y versus X is plotted at a constant pressure of 1 bar. Earlier, we have plotted Y versus X at a constant temperature of 25 degrees centigrade. Normally, we will be using this data to compute the number of stages involved with Pxy method. So in the same way, you should be in a position to plot the Pxy and Txy diagrams even for other systems. For example, if you want to do that, let me create me okay, delete this, back to binary, and take the other components. What is the second system? Okay, let me take chloroform and probably tetrahydrofuran. But remember, the property methods must be selected appropriately. So instead of Chavo said that these are supposed to exhibit a lot of non-ideality in the liquid phase. So let me take something like uniquad for representing the property model for this system. Right? Then once again, next, binary. Now, remember, we have to define properly chloroform, tetrahydrofuran, and chloroform is taken as the basis. Again, you should be able to run the analysis. Now you can see this system is exhibiting an azeotrope. Remember, these calculations are going to depend on the property model you are going to select. Now you can see if you try to join these two lines, P1 and P2, the line is above the straight line connecting P1 and, sorry, this is Txy diagram. I should have plotted Pxy diagram. So it is going to show positive deviation or negative deviation. It is always better to plot Pxy diagram first. So it is going to form a minimum pressure azeotrope. So if you try to join the P1 with P2 by means of a straight line, P versus X is lying below this. So this is a system exhibiting negative deviation from Raoult's law. So negative deviation from Raoult's law will be forming minimum pressure azeotropes, right? And you can see the composition of this azeotrope, and you can also prepare this Pxy diagram at whatever temperature you want. Let me also look at the results. Now you can see the values of gamma 1 and gamma 2, right, are less than or equal to 1. This is the characteristic of systems exhibiting negative deviation. In the same way, you should be in a position to plot y versus x also. So this is your azeotropic composition at this particular temperature, right? In the same way, of course, you can also create other models. This, so say new. One more calculation I would like to show you. You can repeat for the remaining two examples, the PT envelope. So let me take any one system, probably the same chloroform and THF as we did. Remember, in order to determine the property of any mixture, we need to know the composition. So let me give uniform composition so that the mole fractions are 50% and 50%. If you want, you can specify any other also. Run analysis. You can specify the pressure. Method, because check it out. There was some problem with this temperature and pressure. That's why we were not getting. For this particular system, the two components is MEK and toluene. So what do these two curves indicate? Remember, I have given 50% MEK and 50% Tolvin. So the blue line is going to indicate vapor fraction of 1 and the green line is going to indicate vapor fraction of 0. So as long as this composition is concerned, for example, if I start with 190 degrees or 200 degrees centigrade, now what is this pressure going to indicate? For this particular composition, the blue one corresponds to vapor fraction of 1. So as a result, this will be the vapor fraction 1, this will be dew point pressure. And the green one corresponds to the bubble point pressure. So at this temperature, for this particular composition, you are in a position to determine the bubble P and the dew P. Similarly, for any given pressure, I will be in a position to determine the bubble T and the dew T. These 2 points are going to indicate bubble T and the dew T. So for this particular composition, now we have the entire range of bubble P versus bubble T or bubble T versus bubble P. So this can be obtained from PT envelope. So in the same way, let me show you some more calculations that you will be able to make. Suppose I take a pure component. So take one of these. Now you can choose any property of your interest. You can transfer these thermodynamic properties, all properties. For example, I would like to specify specific heat of pure component at this pressure as a function of temperature. Now this is how the specific heat of MEK is going to vary with respect to temperature. Of course, in the liquid phase. If you want, you can also go back and identify both specific heat in vapor phase as well as liquid phase. Now this is how the specific heat, I think the green one is liquid, the blue one is vapor. So in this way, you will be in a position to look at the temperature dependency of any pure component. Right. Okay. I would like to go into the mixture. Okay. Again, remember when you want to calculate the property of any mixture, the property of a mixture is not only a function of temperature and pressure, but also its composition. Let me take any system. It need not be even a binary mixture. Let us say, for example, 25% MEK, 10% Tolvin, 10% chloroform. So you can have any such mixture, and the moment you give the composition, so you are having every component is having 25%. Now, what is that you would like to calculate? So the properties that you want to evaluate for this mixture as a function of temperature and pressure need to be defined. Say mu here. So it says property set 1. So you will have to select the required properties. For example, ideal gas heat capacity of the mixture, heat capacity of the mixture. Let me select this. Right? And then probably let us say thermal conductivity or viscosity. You can pick up whatever values you want. So all these are generally arranged in alphabetical order. So you can pick up whatever property is of your interest. Okay, for example, you can add something like this. I think let me add one more. Thermal conductivity of the mixture. Say okay. Now run analysis. This is because I think I need to restrict the property sets. Some data is missing. Qualifiers we have to define. So in what phase you would like to calculate? So this is liquid. I'm interested in calculating these properties, whatever you have listed in the property set in both liquid and vapor phases. Let us say. Now everything is addressed. you can this property set and sorry, this is one. So let me take maybe two components. You can add as many components as you want, like what I did earlier. So run analysis. Now you can see this is because of something else. The blue one is going to indicate the liquid thermal conductivity. This one is going to indicate the liquid Cp, and probably these two are going to indicate the other vapor thermal conductivity and vapor Cp max. So this is how you will be, the scales are different for different things. So probably if you restrict to one, you will be able to address how the property of the mixture is varying as a function of temperature, right, at a given pressure. If you are interested in calculating these properties at different pressures, you change the pressure and try to calculate them. So these are some of the calculations that you will be able to do by specifying the components, choosing an appropriate property method. You will be able to plot Pxy diagram, Txy diagram, and for any component, you will be in a position to calculate how a particular property is going to vary with respect to temperature. Same is the case with respect to the mixture. But when you come to the mixture, in order to calculate the properties of the mixture, you need to define the composition. Having defined the composition, you will be in a position to identify the temperature dependency of any property of a mixture, right? And you can also plot the pressure temperature envelope, which is going to give you a representation between bubble T and bubble P for the specified composition of the mixture. So with this, I would like to close this session. You can try maybe the other things